Okay, we will go through some important points in the class 12 physics chapter 11 dual nature of the radiation and matter. Okay, see, when a light falls on a metal, electrons are emitted from the metal. This is known as the photoelectric effect. Okay, this light consists of the discrete elements called photons. Okay, each photon have the energy of hv. H is the Planck's constant, v is the frequency of the incident light. Okay, v is the frequency of the incident light, and the electrons from the metal absorb this energy and emitted from the metal. This works on the basis of the law of conservation of the energy. Energy from the incident light is absorbed by the electron and it is converted to the kinetic energy for the electron. Okay, the kinetic energy of the emitted electron is equal to the incident energy hv minus phi, that is the work function. The work function is nothing but the minimum energy. This is important. Minimum energy required by the electron to come out of the metal. Okay, minimum energy to eject the electrons. Okay, to emit the electron from the metal, this is called the work function. Okay, so that means this incident energy is equal to the kinetic energy of the electrons plus the work function. The work function is equal to h v naught. V naught is the threshold frequency. So below this frequency, photoelectric effect will not occur. Okay, only above and are the equal to this threshold frequency, the photoelectric effect will occur. Okay, so you can also say the energy in terms of the stopping potential. V, this is capital V and this frequency is small v. Okay, is capital V naught. This is stopping potential. Okay, 1 electron volt equal to 1.6 in 10 power minus 19 volt. So this is how that conservation of energy equation. This is the kinetic energy of the emitted electrons. Okay, this is equal to the in terms of stopping potential. This is in terms of the incident energy minus the work function. So pi equal to hv naught. Okay, this is the de Broglie equation which connects wave nature of the light to the particle nature. This is lambda is wavelength. This is the wave nature, and the Planck's constant divided by the momentum. Momentum is a mass into velocity. This is the particle nature. Okay, this connects wave nature of the light with the particle nature. That is the dual nature of the light. So depending on the experiment, they will consider the light as a wave nature and particle nature. Okay, V is the velocity here. See here V is velocity, here V is frequency. Okay, so you should not confuse. So velocity of light equal to wavelength into the frequency. So this work function depends on the material. Okay, the power is equal to the number of photons per second into the energy of the photon. Okay, power equal to number of photons per second into the energy. Okay, what is work function? Here you see the minimum energy. This important term is here minimum. Okay, this is the minimum. So it may take more, some electron may take more energy to come out, but this is the minimum energy to escape from the metal. That is work function. 1 electron volt equal to this much joules. Okay. So this is photoelectric emission when a light of suitable frequency, okay, suitable frequency. So that means above that, above or equal to the threshold frequency only, the photoelectric emission will occur, okay. So that is the important suitable frequency, above that frequency, above or equal. So no electron perimeter at all when the frequency of the light was smaller than the certain. This is okay. I already told you, this is threshold frequency. Below this frequency, no electron will be emitted. Okay. These electrons are called photoelectron and phenomena photoelectric effect. This is the photoelectric effect setup. Here light falls on the metal and this is the electron is collected here. Okay. Evacuated glass tube. And the current is measured and voltage is applied here. This is the intensity of light versus photoelectric current. Remember, this is intensity. Okay, intensity of light increases, photoelectric current increases. Is directly proportional to the intensity only. It is not the frequency. They both are different. So it is intensity increases, photoelectric current increases. So when you increase the voltage, the saturated current increases, and after voltage this current saturates. This is called saturation current. Okay, saturation current. More intensity, more saturation current. Okay, this is photoelectric current. See, look at this for the different intensities. This is called the stopping potential. Important. This is on the negative side of this potential. This is important. This is stopping potential. That means the applied voltage is negative collective potential. Okay, here that stopping potential, when you reverse the polarity of this, so all the electrons will get repelled. That stopping potential is measure of this kinetic energy of the electron. Okay, this plate will that is for the measurement of the kinetic energy. You reverse the potential here so that the electron will get repelled instead of collecting. Okay, that is measured to compute the kinetic energy. E V naught, E into stopping potential is the kinetic energy of the electron from here. So that is important. This is stopping potential. The minimum negative, okay, this is important, negative potential is given to the plate for which the photoelectric current stops because all the electrons getting repelled, so the current will stop. So that is the your stopping potential. So this is for the different intensities. Okay, more intensity, more current, nothing to do with the frequency. So this is how the stopping potential is related to the kinetic energy of the electron. Okay, so this is stopping potential here that is related to the kinetic energy of the electron into this is the charge of the electron E 1.6 into 10 power minus 19 intensity. See here, the stopping potential is independent of the intensity. Okay, that is important. Current only is dependent on the intensity, but the stopping potential is independent of the intensity. So only depends on the frequency. For the given frequency, incident radiation, the stopping potential is independent of the intensity. So this is how the stopping potential varies with the frequency. Higher frequency, higher stopping potential. Okay, this is higher frequency, higher stopping potential. Saturation current is same. Greater the frequency of the incident light, greater is the maximum kinetic energy of the photoelectron. Frequency of the incident radiation, this is of the stopping potential areas. This is the summary. Threshold frequency I already told you. Below this frequency, photoelectric emission won't occur. So, these are the experiments supports the wave theory of the light. Interference, diffraction and polarization. These are supports wave theory of the light. So what is photon? The light consists of the smaller units called discrete unit, the so-called quanta energy of the radiation. HV is the, so this is how the incident light energy, the emitted electrons kinetic energy equal to incident energy minus work function. This is the maximum kinetic energy if possible. This is Einstein photoelectric equation. So here K max is independent of the intensity of the radiation, only depends on the above that frequency. It is independent on the intensity of the linear. This is how this threshold frequency related to the work function. Per a photon of energy, momentum. These photons are electrically neutral, okay, not affected by electric and magnetic field. A monochromatic light of frequency is given, okay, incident frequency is given, the power is given. What is the energy of the photon? Okay, E equal to HV. H is flux constant, V is the frequency. Frequency is given, okay, incident light. So this is the energy of the photon. They are asking, okay, this is the energy. Is the in the light beam how many photons per second? Okay, they given power equal to number of photons per second into energy. You have computed energy, the power is given, P by E is the number of photons per second. The work function is 2.14 electron volt, that is pi is given. Find A the threshold frequency V0 they are asking. So V0 equal to this pi equal to HV0, V0 equal to pi work function divided by the flux constant. So this is the threshold frequency. So here important, frequency is less than this threshold frequency, no photoelectron will be ejected. Okay, threshold above that frequency or equal to the frequency only photoelectron will get emitted. Okay. A threshold will be wavelength of the incident light if the photoelectric current is brought to zero by this is stopping potential they have given. So this is the equation we related to the stopping potential energy, that is equivalent to the this energy. Based on the after simplification you will get the lambda, that is the wavelength. Wave nature of the matter, okay. These phenomena support the wave nature, whereas this photoelectric effect and the Compton effect they support the particle nature of the light. Okay, de Broglie connected these two nature of the light and came out with this formula. So this is wave nature lambda. Momentum is the particle nature. He connected both of the nature of the light. So it depends on the experiment how they consider light as a particle or wave nature. Okay, this is the equation. Planck's constant divided by momentum equal to velocity of light by the frequency equal to lambda. Okay, you can use one of them based on your what is given in the problem. The wavelength of the photon is equal to the wavelength of the electromagnetic radiation. So based on this, less wavelength means for the when mass is more, then wavelength will be less. Okay, see here lambda wavelength and mass is inversely proportional. Okay, more mass means less wavelength. So that is given in this also. Based on the mass, what is the wavelength? Okay, wavelength varies with the mass. So the Bernoulli wavelength of the electron is comparable with the electrons. However, for the when mass is more, the wavelength is very less. Size of the quite beyond the experimental measurement. So we cannot measure in the experiments. That is so small wavelength. So here also again the work function. This conservation of energy, light energy is converted into the kinetic energy of the electrons. Okay, the photoelectric effect. Okay, for a given frequency of the incident light is independent of the intensity. Stopping potential is independent of the intensity. Photon, what is a photon and the energy of the photon? So this is the equation. Kinetic energy of the electron equal how it is related to the stopping potential, how it is related to the threshold frequency. These are the Planck's constant and dimensions E equal to hv. So this is how the stopping potential related to the kinetic energy. Kinetic energy related to the incident energy and work function. This is the threshold frequency, how it is related to the Planck's constant. This is a wavelength and momentum relation. Okay. Okay, we will go through the exercise problem. Find the maximum frequency and the minimum wavelength of the X-rays. So this is the kilovolt of the electron they are given. This is the potential of the electrons. Okay. So this is given 30 kilovolts. Okay, 30 into 10 power 3 volts. Okay. So this is charge of the electron. So this is how the electron potential is related to the energy. E equal to EV, charge of the electron, into the voltage they are given. So this is the energy of this electron they are given. So now we have to find out the frequency. E equal to hv, Planck's constant in the frequency. So V equal to energy by Planck's constant. Energy is this given, Planck's constant. So this is the frequency. Now after that they are asking the wavelength. C equal to lambda V. The lambda wavelength in the frequency. Lambda equal to, so the frequency is we found the frequency here. Velocity of light 3 into 10 power 8 meter per second. After substituting you get the lambda. The work function phi naught is given 2.14 when a light is frequency V is given, is incident on the metal turbid, photo emission occurs. So what is the kinetic energy they are asking? Okay, stopping potential and the maximum speed, the kinetic energy. Okay, of the emitted electrons. Say given and they given 2.14 electron volt frequency given. This is joules. Okay, K kinetic energy equal to hv minus phi. Phi is given, Planck's constant, frequency they given. This is the incident light frequency. Okay, frequency, this is Planck's constant, 6.626 in 10 power minus 34 into the frequency. We are converting this into the electron volts, minus, because here electron volts is there, so we are converting so that we can subtract with the same unit. So this is the your kinetic energy is this many electron volts. Stopping potential, kinetic energy related to the stop in this equation E equal V naught. So the stopping potential V naught equal to kinetic energy divided by the charge electrons. Okay, so here we are converting into the electron volt. So this will cancel out. This is voltage, stopping potential. Maximum speed of the emitted photoelectrons. So kinetic energy we know half mv square. So from that we can compute the velocity. So, okay, this is the speed. The photoelectric cutoff voltage, this is stopping potential is given. What is the maximum kinetic energy of the photoelectron emitter? From stopping potential, EV naught is the kinetic energy. 11. EV naught is the kinetic energy. Okay, stopping potential is given. Charge of the electron 1.6 10 power minus. So this many joules is the kinetic energy. Monochromatic light of where lambda is given, the power is given. Find the energy and the momentum of the photon light. Lambda is given, power is given, E equal to hv. V, frequency, is equal to speed of light divided by the lambda. So the energy, this is the energy, and this is the momentum, de Broglie's equation, Planck's constant divided by the lambda. Lambda is given. Okay, this is the momentum. Power equal to the number of photons in the energy of the photon. Okay, number of photons equal to power divided by the energy. Power is given, energy we found. Okay, then you will get the number of photons, this many per second. So the momentum equal to mass into velocity, V equal to P by M. See, mass of the electron, mass of the hydrogen atom. Okay, so velocity, from that we can find the velocity. Mass of the hydrogen atom, they are asking how fast does the hydrogen atom has to travel, velocity of the hydrogen atom. So we are using the mass of the hydrogen atom. Mass of the hydrogen atom. In an experiment photoelectric effect, the slope of the cutoff voltage, okay, that is stopping potential, versus frequency V naught by V, the slope is given. Calculate the value of the Planck's constant. This is the stopping potential over the frequency they are given, that is the slope. Okay, so hv equal to EV naught, then V naught by V equal to h by E. So h calculate the flux constants. Okay, H. So H is computed from the given value. The threshold frequency. Okay, threshold frequency, light frequency also given. Predict the cutoff voltage, that is stopping potential they are asking. So this is the velocity of the electron, stopping potential, and this is the relation. V naught is the threshold frequency. Okay, this phi naught equal to HV naught. Phi naught equal to HV naught. Work function equal to flux constant in the threshold frequency. Okay, so from this equation we can find the stopping potential. Stopping potential. This V naught. The work function of the, that is phi naught, is given. Will this metal give the photoelectric emission of the incident radiation? Okay, of wavelength, this much wavelength. Okay, given the work function, or that is the minimum energy required. Okay, so the energy computed, E of the photon is this. Okay, this is the photon energy, that is less than the work function. So when it is less than the work function, the electron will not get emitted. Okay, should be more or equal to that, only electron will get emitted, no photon will get emitted. Okay, because this energy is less than the work function. Light frequency, this is the speed of the electrons, V, velocity of the electron given. What is the threshold frequency? That is V naught they are asking. Threshold frequency. Again we use this equation. Kinetic energy of the electrons equal to incident light energy minus the work function. So from this, given the value, then we can find the V naught, that is the threshold frequency. This is the mass of the electron. Okay, on this equation we need the mass of the electron. Light of wavelength lambda is produced by the laser, which is photolith. Okay, and the stopping potential they given. Lambda is given, stopping potential is given. Find the work function. Pi naught equal to h v naught. Okay. Minus incident light minus the work function equal to E v naught, that equation. From this we can find the work function. V frequency is equal to speed of light divided by the wavelength. For this V we substitute this. What is the de Broglie wavelength of this for various masses they are asking? From this you can conclude that more mass means less wavelength. Okay, Latin. So you see here, for this mass, and this is the wavelength. So here the speed is more. Okay, here speed is less, and this is the wavelength. Lambda is inversely proportional to the mass. So the wavelength of electromagnetic equal to de Broglie wavelength. Okay. So this is the de Broglie equation. How he related to the electromagnetic wavelength of the electromagnetic radiation. You see, that is the wavelength of the photon is equal to the wavelength of the electromagnetic radiation. Okay, from this, how he derived this, you can go through this. Okay.